Hello, and this is the record for the final practical exercise number 8, which is going to cover the RAKE receiver, which is also one of the possible solutions which we can use to fight the inter-symbol interference, even without using any equalizers, and it also has some benefits, uh, which we will talk about short introduction before the practical exercise itself, and then we will cover the practical exercise tasks. So here is a little bit differently formatted file, requirements with parameters, but nonetheless the idea is still the same. You have some individual parameter, mostly the impulse response. Now, as you can see, the impulse response is quite long, so we really wouldn't want to use, for example, Viterbi algorithm for such system, because it is, well, difficult. Yes, it's 10 samples, so if we use the Viterbi algorithm, we might need which would be, even for the binary system with a base 2, we still would need 2 power of 9 samples, states, which is 512 states. That is a lot, yes. Needless to say that as we change the modulation type to CAM16, it will double and grow up with next higher order modulation type. So here we are going to use another approach. We are not going to use any kind of equalizer at all in this practical exercise. Still, nonetheless, as you will see, we will get quite good result. How? That is about today's practical exercise. So what we want to do here is first of all to simulate the channel with Rayleigh fading and this impulse response you have. Then send data through this channel. Yes, basically that would be part 3. And accordingly receive that data by using RAKE receiver. So we'll talk about specific steps, more details once we get there, but the idea is that after we receive the data, we want to count the number of errors, just like in most of our practical exercises, and plot the picture of error probability or bit error rate, more precisely, versus the signal to noise ratio. Yes, accordingly, typical noise immunity picture we have been picturing so far. This is the list of what you need to include in your report. Mainly these are plots for the channel impulse response, logarithmic amplitude frequency response, transmitted signal constellation for each specified impulse response. So we will have 3 types of impulse response. This, which is originally given to you from 10 samples. Then we are going to make a shorter version with 6 samples, and even shorter with 3 samples out of this initial. So 3 samples of impulse response, that would be this impulse response. 6 samples, accordingly this one. And finally the full impulse response also has a version. We will do this to actually make sure that in this condition the longer impulse response actually is good for us. It is better to have longer impulse response, and the longer it will be, the more energy our RAKE receiver will be able to harvest, and as of such, the better will be the performance. Although with the previous equalizers, Viterbi algorithm, even decision feedback equalizer, you could see that this is actually opposite. Yes, the longer impulse response, the more and more problems we are going to get. Still, here it works somehow differently. Finally, of course, we want to see lots of channel response, bare plots for signal to noise ratio for all of these cases. Yes. So before we get started on the practical exercise itself, let us have short reminding to you what happens, why do we need this RAKE receiver, and how it really operates. So let me briefly remind you that the main issue we are fighting is inter-symbol interference, and it is happening because the received signal travels or propagates via different paths. Different paths have different time duration, yes, so direct wave is the fastest path and it arrives the first. All the other paths take a little bit more time to travel, and as of such it leads to some delay, yes, between a received signal, well, real received signal, and these copies. Also these copies, because of this different diffraction effects, reflection effects, suffer, their amplitude changes, their phase changes, and so on, so they are not exactly the same copies of this signal anyway. Still, we can't do really much about it, except that what we are going to get at this point of reception is this composed signal. We can't split it into multiple components and say, okay, I just want this one and please no these ones. It is unfortunately impossible. Yes, we have to deal with this signal. And so far we've been doing so by designing some equalizers, yes, which would accordingly reverse effect of this happening. So this is fading, and here you can see the example of fading in the amplitude frequency response. That was the result of this specific situation. Yes, so that is the problem. Now we have been so far multiple times simulating this channel, Rayleigh channel, as a finite impulse response filter. So we specified some impulse response. In this particular case of this picture, it's specified as A0, A1, A2. Yes, so impulse response with 3 samples. That's exactly those numbers we've been using for Viterbi algorithm, direct feedback equalizer, MSE equalizer, yes, and so far you always had around 3 values in your impulse response as well. Yes, so this is the diagram that actually shows what kind of channel equivalent model we can have. Here you can see the direct path, that would be for A0, and 2 reflected paths, that would be according to A1 and A2. So since the reflection actually makes the signal travel another path that is geometrically speaking longer, it would lead to additional time required by this traveling. Yes, so basically tau 1 is greater than tau 0, and accordingly this tau 1 is the difference, the delay between the direct signal copy and the reflected signal copy. So depending on the distance of this house, it may be even further, this time can also increase, yes. So this would leave, accordingly, this is the path that arrived the first, this is the next arrived path, and this is the final arrived path, so which was the longest to transmit. So far we have done this multiple times. As of such, when you transmit quadrature phase shift keying signal in such a channel, as you may have noticed in the previous practical exercise, what's happened is you get smaller constellation copies around your real point, yes, and even if we don't have noise. If we have noise, this of course will be smeared and so on, but at any rate, this picture should already see somehow familiar for you for previous practical exercises. What we do next is we add noise with specific noise spectral power density, yes, and 0 divided by 2. In ideal channel, ideal in the sense of impulse response, yes, Nyquist impulse response channel, we have small clouds of the received signals around the center of real symbol, and the higher is noise, the bigger these clouds get. They can start overlapping, make errors and so on, but still, if the signal to noise ratio is good enough, we can clearly separate them visually, yes. In Rayleigh channel, for the same signal of noise ratio, unfortunately it's completely impossible to tell these boundaries between these clouds, yes, of received signals. So, as I said, we are going this time try to use the RAKE receiver to actually receive this signal with as little errors as possible without using any kind of equalizer. That is our goal for today's practical exercise, and it is possible. So, what exactly is this RAKE receiver? Well, actually, this is resembling the tool that is called RAKE accordingly, yes, which the idea is to harvest some, I don't know, leaves or whatever else from the ground when you try to collect them, remove them, and do whatever else. So similarly, these RAKE receivers harvest the energy of the signal from all received copies. That is very important. We are not going to say what we want to do is to somehow try and eliminate these fake copies of the signal. We don't really want to do that, because actually what happens in the sense of transmitting data is that at this point the transmitter is having some kind of energy per transmitted symbol. Well, let's say energy of the symbol. Now this energy is distributed as further and further your signal transmits, the less and less energy is to this point. Yes, so basically what we can say is this energy of the symbol is distributed in this sphere. Well, not really maybe exactly sphere for the real antennas. Still, we need to consider some, I don't know, some area, yes, of the effect of this antenna, and specifically at this point we are going to get only part of the energy. The same part as would be here, traveled by this path. Yes, it also has part of the initial energy. It also has part of initial energy, and this also have part of initial energy. So we don't really want to skip on this energy, because otherwise, if we do, we would have to deal only with this energy. However, this is the same signal that we are actually wanting to receive. Yes, it is a little bit delayed. Yes, it actually makes it more difficult for us to receive because they interfere. But if we were able somehow to separate them and make use of all that energy in total, then that would increase the overall power of the received signal, and the noise, which is otherwise the same if we would have just one copy of the signal, or you have all of them merged together, yes, would be easier and smaller on this scale. Yes. So accordingly, we are really interested in trying to make use of all of these possible paths. So there is a way, by using this RAKE receiver, to combine them all into output signal. However, again, as usually it was a case of equalizers, we really must know the channel impulse response. Yes, because we need to know what is the delay for each copy, what is the amplification or gain for each reflected, direct path, and so on. Yes, so that we can actually do something about it. Yes, so that is still the idea. The concept itself is quite simple. As you can see, we are going to add some weight for each channel component. Yes, so for the direct path there is its own weight, let's say W1. For the reflected signal 1 there is going to be weight 2. For the reflected signal 2 there is going to be weight 3, and so on. And we are going to multiply this received signal copy, yes, with a weight accordingly, yes, and add everything together again. So basically we can say that in a sense we try to split this signal into fragments, not fragments but paths, apply weight for each path individually, and again merge them together. In reality, of course, there is no way for us to split it, yes, and what we are going to do is actually going to be a little bit more complicated. However, the idea is still the same. Each of these paths is going to get its own weight. And then we combine everything, yes, and accordingly we get the result. So here we are going to not simply transmit data as we did before. Before we simply generated some symbols and transmitted them as they are. Here we are going to use a spread spectrum approach, yes, to generate specific code for each bit. So for example, this would have been +1, all of this code fragment, yes, and this would have been -1. Well, just for example, yes. Now instead of the symbol itself, well, this would be again +1. We would send the entire code word that represents this symbol, and we'll do so for each of the transmitted symbols, yes. So this actually will allow us to try and mm, merge them together. Yes, so accordingly, these paths then are going to become, in a sense, how we can say, separatable. Yes, as a code, we are going to use a maximum length sequences. Yes, so but before that, let us actually follow this link. It has a little bit more additional information on maximum length sequence, and also I have added additional link information on spread spectrum systems that you may find useful if you didn't have much of this in your previous other types of courses, but I do think that at least somehow it should have been mentioned somewhere. Yes, still, in the interest of this practical exercise, I'm going to briefly give you the idea of the concept, what it actually does. So normally, yes, we have some signal with some specific narrowband spectrum, which has specific energy. Yes, we then use different kinds of filters. Yes, we use some filters to separate frequencies, we use some filters to shape the pulses, and so on. But at any rate, we somehow follow that we have noise, and outside of our signal, well, useful signal spectrum, yes, we try and suppress all this noise as best as we can, because the noise power spectral density is in infinitely large frequency range. Yes, this is a very small noise power and zero, which we calculate, yes, in our simulations, but the bandwidth of this noise is infinitely large. Yes, so this is the way how we deal with it, by suppressing everything that is outside of our useful band. That is the normal transmission process. Now, for the spread spectrum system, we actually are going to intentionally convert this blue signal spectrum into a much wider spectrum, represented by this red line, which has still the same energy but much more bandwidth. As of such, you may see that actually it will cover much wider band, and it will also take more noise along. So you may think that actually this will lead to problems with receiving this signal. However, I will tell you it's actually possible to design a system in such a way that your spectrum of the useful signal would be so wide that it will be beneath the noise level, meaning that there will be no way to tell if you are transmitting something or not, unless you know how to receive such a signal, and accordingly this is considered as a secret transmission, yes, in a sense. And the best thing about it is, if you happen to know special code that can be used to achieve such spreading of the spectrum, then you can receive this signal. If you don't know this code, then you will not receive this signal, and you may not even be aware that there is a signal at all. Yes, so at any rate, you need some kind of code. Now, once you will apply the code to the spectrum, to the signal, it will again, well, we can say the spread itself, yes, and it will be just as it was before. Yes, so this is a reversible operation, and you can use the same code again to recover the original signal spectrum, and then process it as usually. Yes, pay attention here that since the noise doesn't have this code, it will not be affected by this effect. So actually what is going to happen is the spectrum of this signal is going to despread, and the spectrum of the noise is actually going to be more spread. Well, this is nothing for the white noise, yes, because white noise already has an infinitely large spectrum, but if you were to somehow fight some unwanted, or we can say intentional jamming of your signal with this, yes, that would normally try to jam part of your signal spectrum, then this artificial jamming signal would be after this spreading operation for your signal. Actually, for this artificial jam signal, it would act as a spreading, and it would minimize its effect on your signal. So this actually is very important for military use, yes, where you actually try to jam signals or vice versa to be not jumped. At any rate, this is possible thanks to using some specific code words, such as, for example, maximum length sequences, M sequences, yes, which we are going to use in this practical exercise. So the M sequence is generated quite simple way. You have some shift register, yes, and between these shift registers you have some additions, matters, yes, and the feedback from the output of this M sequence generator feeds the same symbols over and over again to this shift line, yes, and you add well, it feeds to the beginning of this and to not all, but to some of these other flip-flops, yes, for example for this, and for example for this, but not for this. Yes, so for some it feeds the same signal, so it adds together and generates a specific sequence. Now the good thing about this sequence is that it has a remarkable correlation properties. Yes, so the cross correlation of the sequence with its own copy shifted by different positions leads almost to zero. Yes, almost to zero if it's repeated periodically. And if we have no shift, no mutual lag between these copies of sequence, then it gives a maximum. It's a very similar to what we try to do with delay detection for direct feedback equalizer in previous practical exercise. Yes, there we used cross-correlation function between different sequences, which, well, we assumed under normal operation would have to be the same, yes, but because of noise it may not be so. Here, however, we intentionally take the same sequence twice and calculate its correlation function. I will show you during the practical exercise how the real cross-correlation function for this sequence would look if we don't repeat it periodically, and you will see that it still produces the maximum value at the zero sequence. This actually is very good for us, as it will allow us to make a search, yes, for the sequence. So consider we have this sequence. This is our M sequence, and what we are going to do now is to try and also we have some signal here which would be -1, let's say like this, +1, and what we would do is now to try and say here in this path 2 where exactly this sequence is inside. Yes, so what we are going to do is to compare these two symbol sequences like this. The correlation function autocorrelation ACF, yes, function would be low, so this definitely isn't match. Yes, well, it doesn't. So we are going to shift our M sequence and try another lag. For example, for this. They still don't match. Once we get to the position where they will actually be the same, your autocorrelation function will indicate you that this is the true position and that your symbol starts actually here. This way you will learn that this path has been delayed by 2 positions, yes, which is very useful for us, as this allows us to somehow separate them. Yes, so we are going to use exactly this approach in practical exercise. Finally, about this weight, yes, so the concept is very simple. Consider you have impulse response of H1 and H2, only 2 taps of the impulse response, and you have accordingly 2 paths, one with a H1 gain, another with a gain of H2 and a delay. Yes, accordingly what happens in our RAKE receiver is that the first path is going to be multiplied by weight 1, the second path is going to be multiplied by weight 2, then we add them together and we have our, well, we can say almost recovered signal. Yes. So for more details, again, I would advise you to follow this link. Yes, it has some more mathematical background as well as idea, and also how to calculate these weights. Yes, so basically, in a sense, they are almost the same as your impulse response, except for one thing. Your impulse response may be actually a complex one. This is particularly true for the quadrature amplitude modulated signals, yes. But since we are going to use them as a real function, yes, so this complex conjugate doesn't do anything. The complex conjugate changes the sign of imaginary part to opposite sign, yes. So if it was, well, let's say if you had a complex number a plus bi, the complex conjugate would be a minus bi. However, this is no effect if b is equal to 0. We don't really care then is it conjugate or not, but still under concepts correctly it would be to use a complex conjugate here. And the weight is actually ratio of this impulse response coefficient to the energy of the whole impulse response. So you calculate the energy of the impulse response and relative how important is this particular path in the total scheme of these things for this impulse response. Yes, so we calculate these weights, which is quite simple. Yes, and then we apply weights for each path, add everything together, and we have recovered our signal without using any kind of equalizers. Yes, so basically almost we can say this is actually almost equalizing. Yes, almost equalizing. If we were to somehow try convert these into the equalizer, then these weights would be the coefficients of your equalizer. So in a sense it still is something similar. Yes. However, I should add that before we do this, we should despread the signal, so reverse the effect of spread spectrum. Yes. So now for the practical exercise itself. I should mention that we have multiple assumptions here to simplify the process of executing this practical exercise. Normally, in the systems, we have many users, and these users do not necessarily transmit data all the time. Yes, so however, in this practical exercise, there is going to be only one active user, and this user sends data constantly, meaning that it always has either +1 symbol or minus symbol to send, and it never has these silence periods, never sends zeros. That is first assumption. Second, the fading channel, Rayleigh fading channel, doesn't change over time. Yes, so again, we have been so far doing the same in practical exercise for Viterbi, for DFE, so here it remains the same. Now, the impulse response of the channel is taken for granted, so we use it. However, in practice, you still have to find it somehow. Yes, you need to send specific training sequence, analyze the response to this training sequence, and basically find the impulse response. Here, in this practical exercise, we take it for granted and use the same impulse response as we did to generate data. Finally, we are not going to count the energy of the signal. We are going to assume that the energy of one bit is accordingly 1 watt. Sorry, not watt, but joule. Yes. So, with all this in mind, we are actually going to get multiple bit error rate plots versus signal to noise ratio, well, basically bit energy versus noise power spectral density for different number of stars. Yes, so if you have one star, only direct star, your simulation result would look like this. If you have 3 stars, it would be this. For 7, or wait a minute, 6, why 7? It would be 6 stars. And for the 11, no, wait a minute, 11, why is it 10? I believe it was 10 impulse response, but we will count that. Maybe my mistake is that impulse response length is 10. At any rate, it will be the best. So here you can see the more reflected and so on copies of the signal you take into consideration with RAKE receiver, the higher and higher the energy becomes, and the easier and easier it is for this receiver to make a correct detection, yes, to have less probability to error, to make a mistake. Accordingly, finally, here we will also try to show the ideal channel bear. That would be your bonus task, yes, for this practical exercise, which would be calculated in accordance with this formula, yes. So let's get to the practical exercise then. I have prepared a similar way as for previous practical exercise and template for you that you may use and accordingly fill in missing parts, because the program itself is going to become quite big. It is already around 200 lines of code and we are going to add more to it. Yes, so well, mostly they are commands, as you can see, for your better understanding. Some fragments responsible for the outputting data, yes, this is picturing, yes. Still, I believe it would be better for you to focus specifically on the task at hand, not on more like how to plot this picture, how to change the color of that line, and so on. But if you will be interested to see how I achieved such visual effects, you are always welcome to study the code, how I change marker color, and so on. So, first of things we are going to do is to specify our impulse response. So, you need to take one which is specifically for you. Yes, I'm going to use some other which I already have prepared for myself. Yes, and put that in the code. So this is the impulse response of the 10 samples, 10 paths accordingly. Yes, now if in the task you have seen that you will need to use a shorter version of this impulse response, we are going for this purpose uncomment this line or this line. And finally, the ideal channel, ideal impulse response of a channel is just one. Yes, so we are going to simply uncomment one of this line, depending on what channel impulse response we want to simulate. Next step would be the following. So, as you remember in the previous practical exercises, we always had the one parameter n, let's say 1 power of 6. And I was telling that it is quite difficult to get, let's say, for example, 8 or 9. It would simply lead to running out of memory on your computer, and it will say, no, I can't continue, so there is no way for your simulation to actually do this. So in this way, we are going to approach this a little bit more differently, as we cannot simply specify 1 million of symbols as is requested per practical exercise. So here you can see that we need to minimum numbers of symbols for simulation to have 2 millions of bits. We are using a QPSK modulation type, so that would produce 1 million of symbols, each for 2 bits, which still is quite a lot, considering we are going to replace each of these bits with a M sequence of length 31. So actually this is going to produce a 60 million of bits. Yes, and your simulation may not run so well in that case. So for this reason, we have decided to split this large value of n, which would be 1 million, into two fractions. First is going to be a block. Yes, so we are going to simulate it by blocks. So that will be n number batch per batch. So in this practical exercise, I try to show you the approach which we can use to generate for any number of symbols. If you desire to, you can set this number to billions and trillions, let this simulation run for weeks, but still it would work, yes. Accordingly, this is one batch, which is very similar to this number we have been using previously. So in our practical exercise, we are going to set this to 1 power of 5. 1 multiplied by 10 of the power of 5, yes, because this is the most we can safely put, otherwise I am not really sure if it will work correctly, or if on your computer it will have necessary amount of memory or whatever else. If you happen still experience problems, you may put this to 4, then you will need to accordingly increase the number of batches, yes, so batch number is going to tell how many times should we repeat generating this batch. So in our sense, if we want to have a million, then we say that batch number should be 10. Yes, so we need to run 10 batches, 100,000 per each. Accordingly, for the debugging and showing purposes, I'm going to put batch number to 1 to make the simulation run faster, but don't forget that in your report you actually need to set this to 10. So, to make it faster, I'm going to put it to 1. Next step would be to analyze the length of the impulse response. So that is length of h. We did this multiple times, so I'm going to copy and paste this without further explanation. It's really simple, yes, what is happening here. So the next thing is task 1, for which you need to obtain the plots for the impulse response, individually specified in parameters above, logarithmical amplitude frequency response, and 5 thousands of binary symbols transmitted, displayed on the constellation map. Yes, so here we are going to get the results. So all that is relative to the drawing itself is actually already complete. Let me actually try and run this code. I'm going to set some breakpoint. I'm not sure if it, or maybe if it runs. Yes, it does run. So here you can already see the impulse response, but no amplitude frequency response and no constellation map. Yes, so accordingly we need to fill in the remaining parts that will calculate this amplitude frequency response and will generate some data, send it through channel so that we can display it, and also add some noise. So let me check. Yes, there is some error, but it's not important. Our program went long enough to show the pictures. So the task 1.1 basically, yes, is automatically achieved for you as the ones when you type in this impulse response. So let me actually count. What is L? L is 10. Yes, so there are 10 paths. Okay, so next thing is that we need to calculate the logarithmic amplitude frequency response. For this purpose, we are going to use a well-familiar function for you called RAKE for the impulse response h and the denominator 1. And we here need to specify some frequency range. This frequency range is going to be normalized from 0 to p. Yes, we multiply p here, so then we need to generate this range as from 0 to 1 with a step, let's say 0.01, yes, up to 1. So this is the range of normalized frequency. Now 1 corresponds to the Nyquist frequency for the digital process, which in this function FREQ-Z is expected to be p. So therefore we multiply it intentionally in addition to that to p. And we are going to use this frequency from 0 to 1 to show a picture, yes, of this. So then we calculate absolute value of this amplitude frequency response h, which has been obtained by Z transform from your impulse response, and multiply it by 10 and the logarithm of 10. Yes, so this way your amplitude frequency response is now also calculated, but yes, and it has been displayed. So here you can see the amplitude frequency response of your channel impulse response, yes, and analyzing these we can see that it's not really bad. It's just that well, it attenuates the signal. So if our desired spectrum would have been in this part, some part of the spectrum would be amplified, some part would be accordingly even having some fading, yes, at this frequency, for example. As for noise, the noise is accordingly suppressed more or less by this channel. This is unlike the channel we had in the practical exercise 7, yes, 7. And accordingly here you may realize that we talked about some channel that I called very bad. Now you can see why this channel is very bad, because normally our signal relies within here, yes, and as you can see this channel doesn't amplify our useful signal much, but it significantly amplifies the noise. So the noise is actually getting stronger and stronger the higher its frequency, but the signal is not getting as strong as the noise. So this channel specifically amplifies noise for our signal. And since we didn't use any filtering in our practical exercise, this actually had a big deal. But even if we would use filtering, it would still amplify the noise and the effect of filtering would be smaller. But this is some mentioning that in such conditions we would actually do well to use a filtering, matched filtering, which in practical exercise for simplicity purpose we didn't use. So maybe you had this question and didn't ask, but here I say that actually this needs to use a matching filter in your practical exercise as well. But that would be a very big practical exercise, maybe even course project, so I didn't decide to give it there. So okay, next step is to generate the signal 5000 samples and transmit it via this relay channel. Then we are going to calculate the noise power, add noise this signal, and finally plot this signal with relay fading and noise. Yes, the plotting itself is already done. So here we need to specify that what we want to generate is 5000 symbols, number of binary symbols, yes, bits basically. The signal to noise ratio is specified for you in these parameters, so that is the target value for this picture only, yes. So I have chosen it some number because otherwise if you say use 0 it will be too much noise to see anything. If you use 10 it might be too small noise. So I wanted to specify some middle value for you and to avoid for you to choose it by yourself, because any number would really do, yes, but sometimes it's too difficult to take some number to think which I would use 6 or 7, so I have decided to give this number to you specifically, yes. Not that it does much change, yes, it's simply convenience more for you. So I have, for example, this number, then we need to generate some data, yes, so data is generated by random integer generators, yes. So this randy function generates numbers from 1 to 2, we subtract 1, this becomes 0 to 1, and we convert 0 and 1 into plus minus 1s, yes, into NRZ, bipolar form of pulses. Well, the same thing as we did previously. So this would then yes, this would then require us to convert this into QPSK signal. So how does QPSK signal works? Consider you have data plus 1, minus 1, plus 1, minus 1. Let's say like this, yes? Your QPSK modulator then creates a complex signal which takes the real part, all the odd numbered symbols, so that would be plus 1 and plus 1, and imaginary part, all the even numbered signals, minus 1i, minus 1i. Yes, so now we need somehow to convert this one long row, yes, sequence into a complex sequence, so that actually all the odd numbered positions become real parts, all the even numbered positions become imaginary parts. For this, we are actually going to reshape this vector, yes, so reshape data into two columns, yes. So first, yes, I believe this is a column. No, wait a minute, this is a row. Well, let's check it. Run E and sim. We don't have nsim. But wait a minute, nsim. Yes, we don't have it. It's empty. So first, well, actually, it would be easier for me to just simply run this code, and then I do have now data, right? No, I don't. Okay, I then need to put a breakpoint here, which doesn't want to do. Let's odd. You can't put a breakpoint if you have uncompleted lines and so on. Well, anyway, okay, then I'm simply going to copy this, run it, and see what is data. Data is one long row. Yes, so what we want to do now is to reorganize this long row so that two symbols form one column. Yes, accordingly we want, let's say, 1, 2, 3, 4, 5, 6, 7, 8 to be organized as follows: 1, 2, 3, 4, 5, 6, 7, 8, and so on. Yes. So for this purpose we are going to use a matrix reshape function, specify the original data that we want to reshape, then we specify the number of rows, which is 2, and the number of columns, which would be n symbol divided by 2. Yes, since the total amount of data is n symbol and we say we want 2 rows, it leaves twice as less place for the rows. Now this would produce what was that called? STX, yes, shaped. No, it didn't run. Okay, let me actually run it too in the way we wanted. So all that we need to do now is to multiply these with a, well, actually we should say vice versa. We need have this column multiplied by the row 1 and 1i. Yes, so this way in a matrix multiplication 1 will be multiplied by the first row, 1i is going to be multiplied by the second row, and then they are going to be added up together. Yes, so we use matrix multiplication for this purpose. So we set the symbols 1 and 1i, we multiply it by reshape, yes, and form a complex QPSK signal that way. Next step would be to apply the impulse response of the channel to this transmitted signal. So for this purpose we are going to use the well familiar function called filter. Yes, we set the impulse response here. This is 1 because our impulse response, well, our filter is a finite impulse response and its coefficients are simply the impulse response, yes, and accordingly the signal that we want to distort, yes. Not really distort, to filter, but in this particular case this channel acts as a distortion for our signal. Well, next step would be to calculate the noise spectral power density. Yes, so the noise power spectral density is energy of beat, so I'm going to simply add extra variable here, 1, divided by energy of beat versus the noise spectral density, which in turn is 10 at the power of SNR divided by 10. So that's how we did it previous practical exercises, that's how we do it this practical exercise as well. Finally, the sigma standard deviation of the noise according to the lecture material as well, yes, we did it multiple times, is square root of the n0 divided by 2. Square root of n0 divided by 2. Then we generate some noise, add it, yes, and have our constellation diagram ready. So SRX plus, yes, so this is our signal. Now we need to add noise in the complex form, so we multiply the sigma by random normal generator. We generate random normal numbers in range from 0 to 1, and we generate 1 row and n symbol divided by 2 columns. We do repeat this for the imaginary part and multiply it by 1i and add everything together. So now it should have produced the picture, but it says SRX is undefined at the line 55. SRX. Sorry. Yes, of course, we have S channel signal, not SRX. Yes, so S channel signal, that is mistake on my part, it's fine. Now you can see the distorted and noisy received signals, yes, 5000 symbols, bits, I'm sorry, on this plot. So this plot will go to your report. This is just one plot. You will need to have these plots for these other cases. So if I change the impulse response to 1, just to see what would happen in ideal channel, you would see these familiar clouds, yes? So this actually works correctly. So let's go further. The next task is task 2, and we need in this task, yes, so let's keep track, to generate M sequence, yes, by using the M sequence generator with 5th degree polynomial, and this M sequence will later on be used as the spreading code for the spread spectrum system, yes. So let us then write down some formula, not really formula, some algorithm to generate these shift registers. So this shift register, consisting of that type flip-flops, yes, needs to have, well, generally L flip-flops, where L is the maximum degree of generator polynomial. So we say that our L is 5. So that means we are going to need 5 flip-flops. Well, actually, I'm going to draw the schematic somewhere here. 1, 2, 3, 4, and 5. This is actually this same as, well, more generally LFSR, yes, linear feedback shift registers, but M sequences is just one of the possible cases of this LFSR. So I'm specifically calling them M sequences because it's exactly what we want to generate. So this line is a little bit too long. So what happens is the last output is going to be connected to the input. So this is a feedback, and now we are going to decide if we have somewhere here additions or not. For this purpose we need to know the generator polynomial. It has been given to us that the generator polynomial will be of the power of 5. Yes. So here you can already see the generator polynomial with the power of 5, x5 plus x2 plus 1. So we may as well at once here mention this, yes, that we are going to use a polynomial with the coefficients 5 and 2, yes. So here you can only see x5 and x squared. This x0 is always present in any polynomial, yes, so we don't count it. And accordingly, length of this maximum not length, but the maximum degree of this polynomial is going to be maximum of the poly. Yes, well, we know that it is going to be 5. We just don't want to, if we decide to use, for example, polynomial with power of 7, yes, and all the others, then you would have to change 5 to 7 here, and accordingly also here, which is inconvenient. Yes. Well, this can actually even be not even maximum, but the first element, because the first is always going to be maximum, so it's even simpler and asks less resources. So next thing we are going to do is let's generate M sequence with a starting block of 0, 0, 0, 0, 1. Yes, you need to write in some starting block inside these def type flip-flops. Anything will do except all zeros. Yes, if all zeros are in there at some point, yes, this generation will stop and it will produce just zeros at the output, which is not a random sequence. Yes, maximum likelihood sequence, M sequence, is actually has the properties of random one. Yes. So let's say we are going to use this starting block. Next, we need to, we need to see the structure of this M sequence in our particular case when we have the fifth and second powers in these generator polynomials. Yes, so here we are going to add these summations. Yes, so Well, actually we are only going to need to have one summation because there is no summation here. Yes, there can be summation for 1, for power of 2, or up to power of 3. So we have the power of 2, which is second here. So we are going to add summation here, and to this summation we are going to send this feedback signal. All the others are connected one to another. This is the diagram of our M-sequence generator, which we now need to implement in the code. So let's do this. Say our state first of all. So we are going to make a vector of 5 elements, which is going to be a state of this shift register. Yes, so we'll specify it. State. Initially it's going to be filled in by zeros, r-1 0, yes, and followed by 1. So this way we programmatically say that we need to have, sorry, r is 5, all elements except last one 0, and the last one will be 1. There is another way to do so, to generate all of them zeros, and state end is 1. Whichever is more convenient for you. This is only a matter of taste how to program the same thing. Also we are going to calculate the length of the maximum sequence, so it's calculated as follows. Yes, so sorry, not brackets but without brackets. So 2 power of r, which is 32 minus 1. The length is going to be 31 in our particular case before it starts repeating. So m sequence length. This is also the number of code symbols per transmitted bit. So this is m here, which we need to know if we want to apply the spread spectrum. How many symbols we have here? M was 7. Yes. Okay. So further, we are going to do this in a loop for starting by 1 up to maximum length of this sequence, to the total length of this sequence, yes, and actually I'm going to put that inside of this for loop, because in this for loop we are going to get our M sequence. So first of all, how everything of here happens. So I'm not going to be too detailed, but the idea is that you don't have any inputs here, so the only time you do some input is preparation stage, when you put in this starting block. Yes, once you have the starting block specified, this generator will work on its own without your interference. So what happens each k, so k starting by 1, 2, 3 and so on, this is shifted. Yes, so here first things happening is the shift. This shift is circulating like this, and what happens is that at the same time the last symbol, which would be in our particular case state 5, goes through this feedback, is recorded in the first symbol, yes, and accordingly also is added up together with what was previously state 2 into this. So in this symbol what we are going to get is actually state 2 XOR, so this is not a regular addition, this is addition by modulus 2, so XOR state 5. Yes, so this is how it's actually working. But wait a minute, let me double check if it's correct. I'm a little bit now confused about this schematic. Well, yes, this is the same schematic. So what happens is that this particular position we need to have added this symbol. Well, there is actually another way of all this to implement. Yes, and I believe this would be even better for our way. So we can move this addition slightly in other position. It would still produce the same effect, but the addition will be here. Yes, so we move this addition here, and therefore we know that we have to do a circular shift. Yes, so move everything by one position, and in place of the first one we will need to write in this sum. So that's exactly what we are going to do. So first of all, we need to calculate this sum before we do shift, because once we do shift, what was state 2 will become state 3, and accordingly our results will be incorrect. So first we calculate this XOR, then we do a shift. Yes, so let's find, and also this is going to be the same thing as our M sequence symbol. Yes, by running this. So we can actually, I believe we can, yes, help XOR. XOR 1 1 is 0, XOR 1 0 is this. Yes, we can actually use XOR operator directly here. Yes, so we need to calculate XOR between state 2, or even we can say, can we say that state poly is going to, poly is going to be 2, poly is going to be 5 2, then state is going to be, let's say, 1 to 5. Yes, and if we try to address state by this poly, then it's going to produce two numbers which we then can XOR. No, we can't. We have to specify them separately. So in that case, I'm not going to use XOR. I'm simply going to say that I want states representing fifth state and second state. Yes, so poly. Because your polynomial may have more than two values, right? Where did it go? Sorry. Here you can see the polynomial has more than two values, and you can't use just any polynomial. They need to be a so-called primitive polynomial, just like much in Hamming, cyclic group codes that are used for error corrections. Yes, this is a very specific polynomial that matches certain criteria. It's irreducible, yes, first of all, and second of all, it produces maximum possible amount of division remainders by this for the binom m x power of 31, yes, plus 1. So x power of 31 plus 1 in XOR operation divided by this generator polynomial x5 yes plus x2 plus 1 would produce a remainder 0, and no other binom of any lower power will not produce 0 when divided by this polynomial. If it matches this criteria, it can be used as a primitive polynomial. Otherwise, you will not get the maximum length of your sequence without repetitions. It will be shorter. Well, we will be able actually to demonstrate you that. Why not? It's not that long. So what I'm going to do now is say that I want to add them together, these two states, and find the remainder after division by 2. So that is the XOR operation. XOR can be expressed as the modulus of any number additions, a plus b plus c plus d or whatever else, by 2. Yes, mod 2. So you add them together, divide by 2, and find the remainder. Yes, so that's the logic here. So I'm going to find remainder after division by 2. And now it doesn't matter for me, is there one number, 2, 5, 10 or whatever else. I don't have to individually XOR them with one another and do it in a row. So this is, oh, I'm sorry, I didn't intend to erase the diagram. I hope I can bring it back. Yes, I can. Now what happens is that we may make a circular shift of our state. So our state is going to be circularly shifted by one position. Yes, sorry, that is typo, state. And instead of the first position, on first element in the state, we are going to put in all of this sum. So that is MCQ1. So that's state 1 is going to be MCQ K. So this generates the M sequence, which we may now check. We can even output it, I believe. Here, yes, you can see this M sequence. It seems to be random. Yes, it has almost equal number of ones and zeros. Well, it cannot have exactly equal, yes, because we are having length 31 and there will always be extra. So basically, I believe it was ones, but I'm not sure. Let's check it out. How many ones we have? We have 16 ones and we have 15 zeros. I believe it is so, yes. That is the property of M sequence. Any M sequence is going to have one extra one, not one extra zero. So this M sequence is not repeating itself. Yes, you can see that it starts to repeat, but if we were to generate it a little bit longer, so let's say M plus 5, after the 31st symbol, it would have started to repeat. Yes, so here you can clearly see that these last 5 symbols are exactly the same as here. So it's, if you continue generating it, it will start to repeat itself over and over again. Yes, so we don't want that happen. And it will also happen so if you choose poor generator polynomial. So the poor generator polynomial would be, for example, this with x5 plus x4 and so on. So M sequence will start repeating much sooner than 31 symbol. So let's find where it starts to repeat. And this is here. Yes, it already started to repeat before reaching 31 symbol. That is the property of M sequence, that if you use the correct generator polynomial, it will always be maximum length before repeating. Hence, the name of these sequences, maximum length sequences, are possible thanks to these generator polynomials. So we are not going to use this poor polynomial, we are going to return to normal, decent one. Finally, also autocorrelation function for this M sequence can be calculated by using XOR function. Yes, so again val lag, that will be XOR M sequence. However, we need to convert it into bipolar process, -2 multiplied by M sequence plus 1. Also, we want unbiased. So if you remember, today we specify 2 signals for which to calculate cross correlation. Now, if you specify only one, it will automatically repeat as a second signal this signal. So that would be the concept of autocorrelation function. Correlation between signal and its own copy. Yes. Now we can plot this, or maybe stem lag on x-axis, on y-axis values. Yes. And here you can see that cross correlation function produces maximum at 0, maximum at 30. Wait a minute. Did I change M sequence? No, I didn't. So actually I need to run program now first to get a good M sequence. Now for this now you can see the difference, right? There were maximum somewhere here, maximum somewhere here, and so on, multiple maximums of the same size. Now for M sequence, for real M sequence, maximum will be only 1 and at the lag 0. That is the property of M sequence. Yes. So yes, that is a test to prove that it has actually random in it. Yes, the ideal autocorrelation function, of course, would look like this, 1 and all the others will be zeros. Yes, but well, since we didn't repeat periodically the sequence, and you can even see at the lag 30 it's almost maximum again, well, because it's only one symbol compared. Yes, we need to actually repeat it and fill in the missing parts as your correlation is calculated. But okay, these are details of how correlation is calculated. I don't really know exactly how X-score calculates. Still, what matters the most is maximum is at this position. Maximum is positive, +1, yes? So this is M-sequence generator, yes? Next, we specify signal to noise ratio range, in which we are going to simulate. Here you can see that we are actually also going to measure how fast our program runs, so that you get an impression what kind of data you can put in here and how long it will expectedly run for batch number 10. Yes, you will simply multiply by 10. So this will give you idea of how long this program will run for your final pictures. Yes. Okay, next step we need to do is to calculate the weights for the RAKE RAKE receiver by using MRC method. So once again, let me remind you that we are going to calculate these as the same impulse response coefficients, complex conjugates, divided by the energy of the impulse response. So let's do this. That is a short, simple formula that we need to calculate. Also, by the way, before we go away from here, let us convert M-sequence into +1s and -1s, because we are going to need that anyway. Yeah, so that was a good idea to do it in the first place right here. Yes, so convert M-sequence into bipolar +1, minus and -1 symbols, right? So this doesn't have anything to do with these coefficients. I just realized that we better do it right now while we were calculating this M-sequence there. So for the coefficients, yes, so let us then still write that we conjugate, yes, so conjugate of impulse response divided by the sum of the squares of the impulse response. That would be sum h squared element per element, yes? So these are coefficients of our RAKE receiver that are going to be used. Here then starts the main program of simulating, right? In this main program, what we need to do now is to implement the RAKE receiver. But before that, we actually need to generate some data, convert it into a binary form, add some noise, add channel effect. Yes, so here you can see relay channel simulation. Finally, task 4 here will ask you to make the RAKE receiver. That is the goal of this practical exercise. So let us then generate this data. This general data now needs to generate either 0, 1, 2 or 3, because we have 4 possible symbols. Yes. Accordingly, we are going to generate random integers in a range from 1 to 4. So 4. The number of the symbols is going to be number per batches, and the for loop is organized for each batch. Yes, so in this loop we are going to run, blocks, batches, yes, and accordingly, well, we can actually change this to batch number, not block really. Accordingly, this is now what we program is a single batch with a length of 100,000 symbols. Yes, we subtract 1 because we want to get numbers from 0 to 3, not from 1 to 4. Accordingly, this is going to be binary 0, binary 1, binary 2, or binary 3. We are not going to use a gray mapping here this time, I believe, or will we? I think we will, but okay, that doesn't matter anyway, because we are still going to work with the binary data and as it is, yes. So here we convert these symbols into binary code, yes, so we use for that decimal to binary. Yes, let me remind you that if you use this alone, yes, the result is going to let's say, yes, the result answer is going to be characters. Yes, so we want here to use a numbers, logicals, or whatever else. So for that reason, we do comparison. Is the symbol the same as a character of 1? So once we do this, the answer, as you can see, is going to be matrix of logical values. Now with these logical values, we can actually do some actions, multiply by 2 or whatever else. Because otherwise, if we were to multiply this by 2, this would produce strange things, symbols with codes 98, 96, 98 and so on, yes, which is not what we want. So pay attention to this effect, that this is actually a character, and for that reason we need to convert into logicals, and we do so by relation operators. Is it equal? Yes, so this double equality is check, is it equal, not really assignment as here. Anyway, next step is to convert our data into bipolar pulses, yes, binary data, and well, if we run this, I'm pretty sure it will stop somewhere, but you can see that data is well, basically one long vector, yes. What we wanted to do now for QPSK, similarly as what we did here, yes, is to form two columns or two rows of this data, yes, by using the function reshape. So this is exactly what we are going to do, but well, yes, exactly what we are going to do after we apply mSequence. So I'm a little bit running ahead. So let's now, for now, skip this, and let's just make sure that it is always raw. Yes, so, but I believe, we are interested in bin data. Yes, so bin data is actually two columns. Yes, and after we do this NRZ data, it is a two rows of the plus ones and minus ones, plus ones and minus ones. Yes. Now what we want to do is to make them into one single row. Yes, one single row. So for this reason I use this transpose to convert the how it's called, the columns into rows. Yes, so that now data is in one row. Now we want them all to be merged into a single row. So for this we can use, so let's say NRZ data operator like this is going to collect them by following columns. So this column, afterwards this, and that will produce one long, very long column like this. All that remains is to transpose that to get a row. And we have one row. So first symbol is going to be from the first column, second symbol from the second column. We are going to later on again split that into columns, but before we need to apply the mSequence to these symbols. So we have to really do this forward and backward, yes, to convert in rows, columns all the time to actually have it working. So okay, our data has been generated. Now it is a sequence of plus ones and minus ones in one long row. Then we can apply the spread spectrum code, and the idea of this coding is, yes, that what we do is here, for example, we have 1, here we have minus 1, 1, and the code is plus 1, plus 1, plus 1. Well, I'm going to simply give signs, yes, plus, 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 minus, plus, minus, minus. So what we do is we multiply this symbol with entire of this sequence and place it as our signal. So from this perspective, if we have plus 1, then the sequence is going to be mSequence. If we have minus 1s, then it is going to be mSequence with opposite sign. So here you can see minus 1, minus 1, minus 1, plus 1, minus 1, plus 1, plus 1. It's opposite of this. Yes. So what we need to do is to actually apply the Kronecker multiplication between our data and sequence. So let's do this. That is a cron NRZ data and mSequence. So this will take each data symbol, multiply it with this sequence, and replace one symbol with entire sequence, multiplied by this symbol. So this way we actually achieve the spread spectrum effect. Now what we need to do is again split this in two rows, no, columns, no, two rows, correctly, in two rows, and multiply this by this complex base. Yes, exactly the same way as we did it here. So I'm going to copy this and replace some variables to generate the transmitted signal. Yes, so here we want to STX. Now two rows, but the number of columns is going to be so we have batch size, yes, that is the number of our symbols, and we have M sequence. So in total here we are going to have a num per batch multiplied by M, and since we have here two rows, we would have normally to divide by 2, but we don't, because here we have generated the symbols, yes, and each of the symbols already has 2 bits. So the total number of data here in this sequence is this one, yes, multiplied by 2. Number per batch, M symbols per each bit, yes, and accordingly 2 bits per one symbol. So that would be so. This 2 goes from here. So we have 2 here, we remove this 2. So total number of symbols is still double num per batch multiplied by M. So we perform this modulation. Then we do some filtering with relay channel. Yes, so again 0, or not 0, but STX. Apply the channel. However, here we specifically are asked to provide an extra space for the RAKE receiver that is going to do some shiftings afterwards. So instead of simply specifying the signal, we are going to append some zeros at the end. So the question is, how many zeros do we need? Well, the answer is lying in the impulse response. So if our impulse response is 10 symbols, central one is this node is main symbol, then we need to append 9 zeros. If it is 6 symbols, we need to append 5 zeros. So L minus 1 zeros anyway, yes, and we need to do them in one row. Sorry, I skipped a little bit. So that would be 1 L minus 1 zeros. So we append these zeros so that RAKE receiver can have the space where to shift the data once it processes it. Yes, let me remind you that this RAKE receiver was actually making a shifted copies of the signal. Yes, so we provide some space already there. Okay, so now we have added filter channel effect. Next thing we need to do is to go through all the signal to noise ratios, yes, and calculate the energy of bit, which is specified 1. Next thing what we do is convert the decibels into a linear scale, so like this. Again, this has been done already multiple times, so please revert to the previous practical exercises. Then we express from this ratio the noise power, yes. And finally, we specify the variance of this sigma. However, here I would like to notice a very important moment, that we consider that now we have a spread spectrum, and we don't really want this to affect our calculation. So we have to actually multiply this noise power density by M, yes, to make noise M times stronger, so that it is in line and would produce the same results as if our signal would not have spread spectrum. So for spread spectrum you need to know the spread spectrum ratio, which is in our case the same as M sequence length. So we do multiply it here, please don't miss it. It's also even spreading ratio m specified separately here in a comment. So once that has been done, what we have to do is to add some noise. Yes, so we multiply sigma, we generate the real part noise, which is 1 by m multiplied by number per batch plus L minus 1. Yes, so since we have here appended L minus 1 zeros, so now length of our vector is accordingly changed and we added in that here. Yes, originally length was m with number per batch, but now we are going to add L minus 1 zeros. Yes, so we account for that both in real part and imaginary part. Now we have a noisy signal. Next thing we are going to do is to separate real part, separate imaginary part. Yes. As you see, we don't do any equalizing, and now we are going to receive the signals at once. So previously we were using some equalizer and only then we were using a demodulation. Yes, now we are going to go ahead with the demodulation at once. However, very specific demodulation by using the RAKE receiver. Yes, so now what we want to do is to merge them together, real parts and imaginary parts. So let me remind you that real parts were odd numbered symbols and imaginary part was even number symbols. Yes, so now we need again to split them into columns and merge together. So we are going to do that by making the matrix of these two rows. Yes, this is the first row, this is the second row, this symbol makes a new row. Yes, now we have a matrix of two rows. So then we are going to read them by following vertical priority. So first row, first element, second row, first element, first row, second element, and so on. Yes, so for that purpose we use the unwrapping operator, which we did use multiple times already, RCV data, colon in the brackets. Yes, so this will make a column vector, one long column. So here we need to be aware that this is now actually a column. Yes. Accordingly, next step would be to generate RAKE receiver. No, not generate, but implement the RAKE receiver. And here what we need to do first is to shift the data by the position of the impulse response. Yes, so that is, wait a minute, where was that? This step, this very particular step. So this is for k equals 0 shift, k equal 1, k equal 2, and so on. So as much as impulse response coefficients we have, we need to have a shifted copy for each possible case. Yes, so we are going to do them one by one. Yes, accordingly, for the 1, yes, for the first element we don't need to have any shift. For the second we need to shift by 2 positions. Now because in our received data here we have, let's say, +1 -1, which together in the QPSK was one symbol, one QPSK symbol. Yes, so we have to shift by QPSK symbols. So first QPSK symbol, second QPSK symbol, third. So the step of our shift should be 2 in this particular case. Yes, so this can be organized by making received data indexing of this array. Yes, we start by 2k -1, so that let's see here, k is equal from 1 to 10, and 2 multiplied by k -1 is going to be accordingly 1, 3, 5, 7. So each next starting point is going to be from the next QPSK symbol. Yes, because 2, 4, and all other belong to the first QPSK symbol, previous QPSK symbol. Yes, so here we need to remember that originally we were shifting the QPSK symbol until the end, well, except the double of L -1, yes, which was appended zeros, and well, actually it's not even 1 but k, yes, so 1 would be for the delay 1. So here we don't really want to go outside of the boundaries of this array, yes, because well, we need to have them of specific length. Yes, we need to have enough symbols to find 31 bits. So this total length must be divisible without any remainder by 31, and the only way for us to achieve that is to specifically filter out the symbols. Yes, so this is a little bit tricky part. Yes, why exactly it is so. With the beginning it is clear, but with the final step, well, it's not exactly so transparent and obvious, but you may trust me that this is actually how we are going to achieve our result. So, next step would be quite simple. What we want to do now is to reshape this data so that each column, yes, so yes, each column is one symbol multiplied by sequence. So m sequence. So here we are going to have 31 rows, and the number of columns would accordingly be the number of symbols. Yes. So we need to do a reshape in this sense. So we do a reshape for shifted data array. Now we need to have m rows and num per batch symbols multiplied by 2. Yes, by 2, because now we have not quadrature PSK symbols but binary symbols, and as you know there are 2 bits per one QPSK symbol. So it's now warning me that it's time to conclude because I'm going to run out of space soon. So let us finish this practical exercise. Finally, what we want to do here in this receiver is to first of all reverse the spreading effect by multiplying the same code to our user data matrix, and then accordingly, since now m sequence is located in this array vertically in one column, we need to multiply this as a row, m sequence, so which is already row. So row multiplied by column is going to multiply sequence by the data bits and produce the received symbol. Yes. Now, however, that would produce the row of received symbols, and the next step, what we need to do is to multiply each of these symbols by the coefficient of MRC method, specifically or particular for this shift. Yes, so basically what we do is multiply USR data k this. So this is the USR data column 1, yes, for the direct path. So we are going to multiply this with an h coefficient for the direct path 1. Now, once this k becomes 2, this is going to be the first reflected signal, which would produce the column for the reflected signal multiplied by this coefficient, yes, and so on, so that we process all the 9 reflected signals. Finally, what we need to do is to read this signal, yes, which is actually, well, first of all, we need to add them together. All these columns needs to be added together. Yes, so we need add in accordance with this diagram. Yes, we already have this multiplication done just right now. So what we need to do now is to add all these columns together into one signal. So we do this sum of the USR data specifically along dimension 1. So this is the way to tell it that what we want to do is to sum the columns into one single column. Yes, well, it's easier maybe to show. So we have matrix 1, 2, 3, 4. If I run sum of this matrix A, I didn't name it, so let's name it. Yes, sum of matrix A, it is going to do so by rows, yes, or by columns. So it added 1 plus 3, it added 2 plus 4. What I wanted to have would be 3 and 7, so that it adds columns together. For this reason, I can specify the dimension. So first dimension, wait a minute, and the second dimension would be this. But our USR data, by the way, is it? We didn't run it yet. Let's now just double check. Is it really a column? Because I'm a little bit confused now. USR data. No, it's quite a lot, so let's check it here. It's 31 by 200,000, yes, so 31. No, it is, we want to it is correct, we want them to be added by the row. So it's not necessary even to specify this parameter, but just to be sure that it did so by rows, I'm going to leave it anyway, yes. So now that we have added them together, all that remains is to tell is it +1 or -1 by analyzing its sign. Yes, so if the number is negative, it's going to produce -1. If it is a positive, it's going to produce plus. So the +1, right. Okay, the final step would be estimate the number of errors. So I do believe that we can actually skip but wait a minute. No, we can't. We do need this separate variable to tell us how much errors have happened in this one batch. Yes, and then we need another variable to say how much errors are there for all of the batches. Yes, so generally speaking, then we need to count the specific number of errors and then accordingly add this up together to the batch. So anyway, we calculate the number of errors just as we regularly do by comparing and counting the number of inequalities, yes, mismatches. So that is the number of error per this particular batch. Now what we want is to accumulate this number of errors over all of the batches in this variable nej. So this way, with each next batch, this is going to become more and more accurate. Yes, so as if you have used more symbols for statistics. So basically, this way we address this issue. Yes, sum of number of errors, Okay, so finally, we estimate the bit error ratio as the ratio of this number of errors per number of total transmitted bits, so which would be numbers per batch multiplied by the batch number of batches I mean, and multiplied by 2 because each of the symbols generated per this interval contains 2 bits. Now that we run the program, it calculates and outputs some results and produces the bit error ratio plot for your selected path. Now currently I have what I have would be an ideal channel, yes, with the impulse response of 1. Now you may keep this window or figure open, so it will add more and more plots to the same window. The program has been organized like this already, so I am going to run my initial impulse response to see how many errors there will be, and as well as, let's say, with a length 6 and with the length 3 also. It's not taking that much. However, please pay attention that you are going to need to change number of batches to 10 so that it produces a million of symbols and gives you more reliable statistics. So that would be it. At any rate, it's warning. At any rate, you can see that the more paths we have, the better is actually the performance of this receiver. Well, except for one single path, which is the ideal channel, and no intersymbol interference at all, which obviously should be very close to the theoretical limit. And that is a bonus task for you. You may add this theoretical line, which is available in the formula, but I think I have it now closed. Well, actually, let me try and fast see it, if I can open it. Additional materials, yes, that's available here. This formula would produce this line, yes. I have already it stored in my script, which I can run from the command line, and it will add an extra picture, so you can see this black dotted line is actually very close to this blue line. Yes, so it is, if you want to, you can add this line as well. I will not show how, so that you have something to do. Yes, but you need to run these simulations for million symbols. So either you can change this to 6, which is not advisable because we organized this program in the first place to avoid necessity to use too much memory, so that you can maybe use this computer we are simulating on for other needs, or you can set here number of batches, so it will repeat these short batches multiple times and accumulate statistics in this vector, yes, where we add for each next batch the next number of errors. Finally, here you may notice that it actually ran 3.5 seconds on this computer on total with a batch 1. So you can expect that if you use 10 batches, this number will increase 10 times, so it will be 30 seconds for one simulation. And you are going to need to have 1, 2, 3, 4 of these simulations, so that would be in total around 2 hours, yes. Well, you may try and make some script that will make it possible to run this unattended, yes, so that you simply press the button and for 2 hours your computer runs, or you can accordingly run them one by one, and it will update the picture also. So I will leave it up to you. This was a final practical exercise of this course. I hope that you found something useful in this course, and as usual, if you happen to have any questions, any problems related to this telecommunications theory, you are always welcome to ask me. Thank you for your attention.